Hello again. I've had some requests to do a video about a statically indeterminate torsion problem. That seems like a pretty good idea, so let's do that. Let's talk about torsion real quick. I've got my make-believe drive shaft here. This is actually a swim noodle from a pool, but it's round and it's going to act like a shaft in torsion. I've got a line drawn down it with marker, and you can see as I twist it, that line distorts. That line is not straight anymore, or it's straight, but it's at an angle now. Okay? A statically indeterminate problem is one in which statics alone is not enough to solve the problem. You have to use some other argument. We're going to use one from strength of materials. I can't quite fix both ends of this, but one type of statically indeterminate torsion problem is one in which both ends are fixed and there's a torque in the middle. Well, I've only got two hands, so I can't quite do that, but you can imagine if this end is fixed and that end is fixed and I grab the middle and turn, okay, I've got zero displacement there, zero displacement there, and I've got some angle in the middle. That's the problem we're going to solve. Okay? So let's take a look at this. Let's say I have a shaft. Looks like that. And right about there, I'm going to put a torque. I need some numbers here. So that distance is going to be 400 millimeters. That one's going to be 600 millimeters. And it looks like I got that right. Okay, so total shaft is 1 meter in length, 1,000 millimeters. I need a diameter, so I'm going to make that 20 millimeters. And I need a torque, not quite in the middle, but in between the two ends, which is going to be 500 Newton meters. Okay, so we're talking about a shaft that's about that big around, about that long. So it's kind of a human-sized shaft. It's not gargantuan. The ends are fixed. It's kind of hard to draw fixed on an isometric, but the ends are fixed, and there's going to be some angle in the middle there. All right? Well, let's start this the way we start all strength of material problems. We'll start with a free body diagram, and we'll actually draw a free body diagram of this thing, and I'm going to split it in the middle to show that there are two halves. We can draw lots of different free body diagrams. I'm going to draw mine this way. Okay, so I've got a torque here. And I'm going to call this A and that B. There we go. Section A and section B. So I've got a resisting torque there, a reaction torque, and I'll call that TA. And I've got a reaction torque there, which I will call TB. Right? Well, since the sum of the moments has to be zero, we know that 500 Newton meters equals TA plus TB. All right, so far so good. We've got one equation. The problem is we've got two unknowns. Well, fundamental theorem of algebra is that if you've got two unknowns, you better have two equations. Well, here's where our problem occurs. There are no more statics equations we can write. We can look at forces. There's no forces in the x direction. There's no forces in the y direction. There's no other moments. This is it. We can only write one statics equation, but that equation has two unknowns in it, so we're stuck. Okay? This can't be solved by itself. That's what makes this statically indeterminate. Statics alone won't solve this problem. All right. Fortunately, we know one other thing. We know that the deflection or the torque, try this again. The torsional deflection at that point is the same for section A as it is for section B. So we can go to use one more argument to write one more equation. And let's see, let's say that there's the original line. Let's say I drew a line down this shaft, maybe I'll just use a dotted line to show where it was. When the torque is applied and there's torsional deformation, the shaft twists, we might expect that the new line to look something like that. Okay? So we'll call that angle there theta A and that one theta B, where the angle is that little tiny angle down there. So theta A equals theta B. Right? We know that's true. This is where we're going to get the next equation from. If you remember from strength of materials, okay, there's the expression for torsional displacement in a shaft. Okay, T is torque, we know what that is. L is length, we know what that is. J is the torsion, the moment of inertia, area moment of inertia, for a round shaft, that's pi over 32 d to the fourth. Okay, I'm going to do everything in meters here. And when I do that, I get this eensy-weensy little number, if I can find it here. There it is. 1.571 times 10 to the minus 8 meters to the fourth. Well, why is that number so little? Well, that's because a meter is about that big, and I've got something that's a lot smaller than a meter in diameter, and I'm raising it to the fourth power. Well, you take a little tiny number and you raise it to the fourth power, you get a really, really little tiny number. That's what's going on there. Well, G is a material property. It's the shear modulus. Just like there's an elastic modulus, there's a shear modulus. I need to assign that. I'm going to assume this is aluminum. And so G is 25 GPa. Depends on the flavor of aluminum you use. I think the number I looked up was 25.5, but to keep the numbers round, that's close enough. All right, so I'm going to write this equation out, and I'm going to substitute in. So I'm going to say TA LA over JG. Now JG is the same for both halves of the shaft, equals TB LB JG. Okay? So this is the same on both sides, it can cancel out. Okay, so what I've got now is I've got two equations. There's one, and there's the other one. Two equations, two unknowns. Now I can solve the problem. So I'm going to erase some stuff on my little board here, and we'll go through the last little bit of mathematics. I guess I can get rid of that. Okay, so let's write equation 1 is TA plus TB is 500. That's 500 Newton meters. And this one, now I'm going to put the lengths in here too. So 0.6 meters times TA equals 0.4 meters times TB. Okay, two equations, two unknowns. Let me get rid of this here. All right, well, that's, you can solve it by substitution or however you want. You're going to work this out, and you're going to get these numbers. Okay, TA is 200 Newton meters, and TB is 300 Newton meters. Right. Well, notice that the two lengths are related by the ratio 3 to 2. 6 to 4 is the same as 3 to 2. And so are the torques. So it makes sense. It passes the sniff test. It seems plausible. The last thing we want to know now is, what is theta? Well, they're both the same. So theta A equals theta B. It doesn't matter which one we calculate because of the differences in torques. We're going to get the same angle for both. So let's just use A. So TA LA over JG. Well, that's going to be now 200 Newton meters times 0.6 meters times 1.571 times 10 to the minus 8 meters to the fourth times, let's see, 25 gigapascals. That's 25 times 10 to the ninth. 25 times 10 to the 9 Newton per meter squared. Now, if we did this right, we're going to come out unitless, because when we're dealing with radians, and radians, if you remember, is unitless. It's actually a ratio of distances. I've got another video about that. So if you want to know where a radian came from, go back in the YouTube channel and you see that, why radians are unitless. There's a very good reason. So this answer is going to come out in radians, and it comes out 0.306 radians, and that works out to 17.508 degrees. Now I've used 3 significant figures there and 5 there, so that's not so good. Let me do that. 17.5 degrees. Now, I set this up so that J and G were the same on either side of the torque, but they don't have to be. If you use different materials and you stuck them together, or you've got different size shafts or whatever, just carry the J and the G through for each side. Okay, just they don't cancel out in that case, but that's fine. They don't need to. All right, and just run the problem the same way, and you'll find out you get an answer every time. All right, hope that helps.